Have you ever wondered what the total RMS error is and how it affects your image? Well, today I'll go through that with you. What's up, Beardos? And today I'm going to go over with you one part of PHD2 guiding, which is the total RMS error, and what it means and how it can affect your images. And I think this one is actually really important because, yes, you want to have better guiding. You always want to have better guiding if you're guiding. And unless you buy, a $10,000 plus mount, you're likely going to be using a guide scope or an off-axis guider. So the total RMS error it's basically like, it tells you how much PHD2 is making corrections in your mount. And I had to learn it myself because, learn about it myself because I actually went to the PHD2 two guys in their Google group, and I asked them, a question on how to get guiding down, and they kind of explained to me the relationship between the total RMS error and really the particular setup that I was using, and why it wasn't even worth it to try to get it down even further. So, with that, let's go into the explanation of what the total RMS error is in PHD2.
All right, let's talk about guiding now. What I'm not going to do is I'm not going to go through like all the setup of PHD2. There's so many videos out there on this, but I did want to talk about the RMS error and what these things mean. Because, the assumption is always that the lower the number, the better you get. And that's not always, it is true, but there are diminishing returns, especially as you go to smaller and smaller focal lengths. So I'll talk a little bit about, the effects of this RMS error on your imaging. By the way, like a lot of times you'll see folks will be like, it's a little bit high, but then they go and look and their stars are still round. So there are some diminishing returns. Okay, so let's go through this a little bit. So what do these numbers mean? Basically, the one that's important is the one on the right. The one on the right is how many arc seconds off you are. And that's determined by how much the star basically moves in either RA or DEC. Now, in DEC or declination, once you slew to a target, the idea is, especially with equatorial mounts, that you only have to track in right ascension. So your telescope mount should only have to move in right ascension. The declination, theoretically, shouldn't move at all. But that's in absolutely ideal conditions. So in the case of like you just have a slight polar alignment error or any polar alignment error, which most of us, don't get perfect polar alignment, you'll see some movement and declination that needs to happen in order to ensure that the star stays put. And so you can see here I have some declination movement. Some of it is also from the RA. So once the RA has to be corrected, the declination may have to also be corrected. And then the total RMS error is simple enough. If you remember back from grade school, this is basically, a triangle. So the total RMS error is the hypotenuse of a triangle. So what you do is you do the square of the RA, add the square of the declination, and take the square root of the total, and you'll get the total RMS error. So let's just plug this in and see how it works. So if we take 0.55 or 0.54, 0.39, and we put it in, and let's see what we get. Let's see if we get 0.67. So I'm going to open up here. I've got a sheet, and we'll go here, and we'll put, what did we say? It was 0.56 and 0.43 is equal to 0.7, 0.556, and then 0.43, and we got 0.71, which is essentially, the same value that we have here. This number is how many pixels off it is. Now, this number is a little bit less important because most people are doing guiding with a guide scope. And this is actually based off of the pixel scale of your guide scope. This tells you, and it's the same thing. You take the 0.13, you'll get 0.18. Here, let me show you. 0.13, 0.13, 0.18, and as you can see here, the formula is just a square root of a square and b square, and the same thing here. But yeah, so this will tell you how many pixels off it is. So unless the focal length of your imaging scope is the same or very similar to your guide scope, this number is really, kind of irrelevant. And what you really care about is how many arc seconds off you are. And you can calculate this, you can actually calculate these numbers, and I'll show you the effects of it on different focal length telescopes. So let's go over here, and let me fill this in with the numbers that we have. So if you remember from my other videos, the pixel scale is essentially this magic 206 number multiplied by the pixel size and divided by the focal length of your telescope. And so you can see here, this is my guide scope. It's 250 millimeter length, 5.2 pixel size, and the pixel scale is calculated to be 4.28. Okay. My William Optics GT81 has an ASI 1600 mm camera. It's 382 millimeters with a focal reducer, 3.8 pixel size, and the pixel scale is 2.05 with that formula. And then I'm going to put like the full focal length of my Edge HD 11-inch telescope, even though I never use it without a focal reducer. But this is just for illustration purposes anyway. 3.8 microns for the pixel size. And then we get a pixel scale of 0.28. So let's see what the effects are here. So what we're going to do is I'm going to go and plug this in. And let's plug in this number of 0.8 and see if we get 0.19. So 0.8, and we got 0.19. And the formula is you take the arc seconds per pixel and divide that by the pixel scale. So 0.8 divided by 4.28, and we get 0.19. Now what happens when the pixel scale goes up? So this exact same error for my imaging scope as I'm, imaging tonight, 0.8, you can see that the pixel error is 0.39. So that means this guiding error that I've got, this RMS error, is magnified as I've increased the focal length of the telescope. And what's worse is if I take this exact same guiding error and take it to 2800 millimeters, you'll see that the pixel error is actually 2.86 pixels, which is very high. So what that means is that for larger telescopes, for telescopes with longer focal lengths, the effects of bad polar alignment, the effects of, the mount not being a high quality mount, it can significantly affect your imaging, because what ends up happening here is you get these like football shaped stars that, aren't, well, they're not round, and they don't make the image look that great. A way that you can actually combat that a little bit is by reducing the exposure time on your telescope so that it's not it's not like tracking incorrectly for very long, and you don't end up with these elongated stars. But we'll talk about that a little bit more later. But for now, I just wanted to kind of show you guys the effects of these three numbers. They're extremely important, but always pay attention to this one. Don't pay attention as much to this one unless you're using an off-axis guider. If you're using an off-axis guider, this is a totally different story, because your main imaging scope is the same scope that you're using for guiding. So it's a totally different thing. And right now I'm dithering, so this number is going to be completely thrown off here in a couple seconds. Okay, that's it for now. So I will see you guys later. Thanks.
So that's it. That's what the total RMS error is. And you'll see that with the longer focal length telescopes, the total RMS error matters significantly more. So if you're using a Schmidt-Cassegrain or a Newtonian telescope that has very long focal length, or even a very large refractor, then you really want to, you'll care a lot more about that total RMS error. And additionally, you might need a longer focal length guide scope or the use of an off-axis guider, because with that, it actually makes the tracking more accurate for the longer focal length telescopes if your total RMS error is not too huge. But the main thing that you're looking for is the impact that the guiding is having on the number of pixels on your image and how much it's actually affecting it. And for that, you actually need to do a little bit of that math. Now, it's not overly complicated math. It's pretty simple math, but nevertheless, it's important to kind of know the ratio and know when you're reaching kind of diminishing returns. If you have a very short focal length scope or camera lens, like if you're using a 135 millimeter camera lens, getting half arc second or less guiding isn't going to make a whole lot of difference because it's not really impacting your image at all. However, if you're using something that's like 1900 millimeter focal length or something bigger, then the impact of that is magnified as well, and with that you actually end up needing to have much more accurate guiding to get really sharp stars. Well, if you like these videos, again, always definitely hit that subscribe button. I appreciate it. I appreciate your support, and we'll see you next time. Thanks. Bye.